Hey there. Today we're diving into an explainer of a historic 1989 research paper that literally changed technology forever. So, let's hop in a time machine. We're going back to a year defined by the fall of the Berlin Wall, the launch of the original Game Boy, and honestly, unknown to most of the world at the time, a quiet but absolutely monumental breakthrough in artificial intelligence. We're going to uncover the origins of modern AI vision. See, long before we had algorithms recognizing faces in our camera rolls or driving cars down city streets, researchers had to tackle a really fundamental problem. How do we get a machine to just look at a human scribble and actually understand what it means? The solution to that puzzle? Well, it laid the very foundation for the neural networks running our world right now. To really get the scale of this problem, check out these handwritten zip codes. I mean, these are not your carefully drawn, perfect textbook numbers. This is the messy, totally relatable reality of everyday life. These are actual numbers pulled from envelopes going through the U.S. Postal Service in Buffalo, New York, back in the late 80s. People write with different pens, in weird sizes, with totally bizarre slants, and sometimes, let's be real, it's just total chicken scratch. For a human sorting the mail, sure, it's annoying. But for a computer in 1989, this level of ambiguity was an absolute nightmare. Because how do you program a set of rigid, hard-coded rules to understand a number 5 when literally every single person on Earth draws it a little bit differently?
Okay, let's dive into this. That right there is the core mystery we're unraveling today. How exactly do you teach a machine to read human handwriting? Well, Yann LeCun and his team of researchers at AT&T Bell Laboratories decided to approach this massive real-world puzzle from a totally different angle. Instead of sitting down and trying to write a million lines of code to explain every single possible variation of a sloppy number 3, they wanted to build a system that could look at the data and just learn those variations on its own. They had to somehow bridge the gap between the chaotic, physical real world of handwritten letters and the super precise digital world of computers.
But, before the machine could even attempt to learn, the researchers had to do some basic housekeeping. You can't just feed a raw, chaotic photograph of a whole envelope into an early neural network. It'd completely crash. So first they went through this unglamorous but absolutely essential pre-processing stage. Step 1, find the zip code block on the envelope. Step 2, slice that block up to separate the individual digits. And step 3, and this is really the crucial one, they took each isolated, messy digit and mathematically scaled it down to fit perfectly into a neat 16 by 16 pixel grid. They normalized it. That's a mere 256 pixels total, which is incredibly tiny by today's megapixel standards, but it gave that 1989 computer a standardized starting point it could actually digest. It's kind of like taking wildly different sized photos and cropping them all so they fit perfectly into the exact same picture frame.
Now, this brings us to the really cool part, the innovative weapon they built to actually solve the puzzle. This multi-layer neural network architecture created by LeCun's team is essentially the blueprint for early machine vision. And yeah, it might look a bit intimidating at first glance, kind of like a complex wiring diagram, but it's actually incredibly elegant once you get the hang of it. Notice how it's structured in these distinct, stacked tiers. The information basically enters at the bottom and bubbles its way up through these different hidden layers until it spits out an answer at the very top. So let's break down exactly what's happening at each of these stages.
Let's see how this all builds into a logical flow of vision. Think of it like a factory assembly line for understanding images. Step 1 is our 16 by 16 pixel grid. That's the raw material entering the factory doors. Step 2 is the H1 layer, which is made up of these things called feature maps. This layer's only job is to look for really basic shapes, like a straight edge or a tiny curve. Then step 3, the H2 layer, takes those basic shapes, undersamples them, which basically means it shrinks the image down so it's not so obsessed with exact locations, and starts combining them into much more complex patterns, like a loop or a sharp angle. And finally, all that synthesized information reaches the top, the 10 output units. These 10 units represent the digits 0 through 9, and whichever unit is buzzing the strongest, well, that's the machine shouting out its final guess.
Now, to make that assembly line actually work, without needing an impossible amount of computing power, the team used a brilliant technique defined here as weight sharing. And guys, this was a massive conceptual leap. Instead of having every single connection in the network operating completely independently, they forced groups of hidden units to share the exact same set of weights. So imagine you're a detective looking for a really specific clue, right? Like a fingerprint. You wouldn't use 1,000 different magnifying glasses at once. You'd use one magnifying glass and just slide it across the entire image. That is weight sharing in a nutshell. It creates a single feature detector that scans across that whole 16 by 16 grid, searching for a specific shape, whether it's hiding in the top left corner or all the way down in the bottom right. So the absolutely crucial point here is understanding why this was such a huge turning point in the history of artificial intelligence. On the left side, you've got old hand-coded AI. In those older systems, human engineers literally had to sit down and painstakingly write out the mathematical rules for what a curve or a straight line looked like. It was exhausting and honestly, super brittle. But on the right side, you have this 1989 breakthrough network. Because of the architecture they built, the researchers didn't actually tell the machine what features to look for. The AI network organically learned its own feature detectors just by being exposed to the data. It figured out what was important all by itself.
But how exactly does a machine learn on its own? Well, it happens through a continuous repeating cycle that we can call the learning loop. Step 1, you feed the network that 16 by 16 pixel image of a handwritten digit, and it makes its best guess. Step 2, you calculate the error. Basically, if the image was a 7 and the machine confidently guessed 4, it's wrong, and the system mathematically measures exactly how wrong it was. Then, step 3 is where the magic happens, updating the weights via backpropagation. Think of backpropagation like a teacher correcting a student. That error signal travels backwards down through the layers of the network, tweaking the internal weights, those little feature detectors we talked about, just a tiny bit, so that the next time it sees that image, it makes a much better guess.
And the researchers implemented a very specific strategy to make this teacher-student dynamic incredibly efficient. They used something called online updating. See, in some models, you might show the network thousands of images, calculate the average error for the whole batch, and then make one giant update. But here, using a math technique called a stochastic gradient procedure, the network updated its entire understanding after every single individual pattern was presented. Guess, correct, update. Guess, correct, update. This constant, super-fast micro-adjustment process meant the network converged on the right answers and actually learned the insanely complex nuances of human handwriting much, much faster.
Now, what's really interesting is that we can actually see this learning process proven visually right here. Notice the top graph showing the mean squared error and the bottom one showing the raw error percentage. On the far left, at the very beginning of training, the error rate is incredibly high. I mean, the machine is basically just guessing blindly. But as you follow that curve to the right as it goes through more and more training passes, you see this beautiful dramatic drop. The line just plummets. This isn't just some abstract math happening in the background. This is the literal visual representation of a machine gaining comprehension in real time. And that brings us to a highly satisfying, super concrete payoff. How long did it actually take for this artificial brain to figure it all out? Just 23 passes. No way, right? It took only 23 passes through their massive training set of thousands of handwritten numbers for the network to reach its optimal, robust performance. Just 23 repetitions of looking at the mail, making guesses, and adjusting its weights before it essentially became an absolute expert at reading those messy Buffalo zip codes. Let's look at the real-world results, because ultimately, theory doesn't matter much if it can't survive contact with reality. And these numbers, they were staggering for 1989. On the training set, the error rate dropped to a microscopic 0.14%. When they showed it a test set of numbers it had literally never seen before, it only had a 5% error rate. Better yet, in a real-world postal application, they could set the machine to just reject numbers it was totally unsure about. By doing that, they reached a tiny 1% error rate on the remaining mail. And to top the whole shebang off, running on standard commercial hardware from 1989, we're talking machines with a tiny fraction of the computing power of your current smartphone, this system could process more than 30 classifications per second. It was fast, it was accurate, and it was absolutely ready for the real world. This entire journey, through pre-processing, that layered architecture, and the backpropagation learning loop, leads us directly to this simple but incredibly historic quote from the researchers' conclusion. We have successfully applied backpropagation learning to a large real-world task. That one sentence cemented the legacy of this paper, because before this, a lot of critics thought neural networks were just, a neat academic trick that would never actually scale out of the lab. LeCun and his team proved them wrong. They proved that with the right architecture, an artificial neural network could absolutely tame the chaotic, messy data of the real world. Which brings us to a final, pretty profound question to consider. This 1989 system was a blueprint. It had a few thousand connections and was trained on what we'd now consider a very modest computer. Yet it successfully taught a machine to read human scribbles. So look around at the AI revolution happening right now, today. Today's neural networks have billions or even trillions of connections. They're trained on vast supercomputers, using essentially the entire internet as their dataset. If that humble, brilliantly designed assembly line from 1989 unlocked the ability to read a zip code, what on earth will today's massive networks learn to see next? The foundation was laid decades ago, for sure, but the story of AI vision is truly just beginning.